So when we did the initial wiring and startup on this truck, I used a tack sender that was supposed to work and everything, and hooked it up to a tack that was brand new and everything, and well, the tack wasn't working. So we need to resolve that and get a working tachometer in this thing, because it's very important for a diesel engine and a manually shifted diesel engine like this. You need to know where you're at and what your engine's doing, and especially on this one, because we have no idea what the gearing is on this truck. And when I'm actually out driving it, I've never driven this before. I have driven similar 6BD1 turbo engines, but they're a little different, so I don't know what's going to happen. I need a tachometer. Anyway, that's the goal of this video. Let's get into it. I believe I found a sender that will work with a variety of tachometers available today. It's a pulse sender. The way the tack works is it takes that pulse, you set it on your tachometer. There's buttons that you can set up, and you set the pulses per revolution, and then it'll translate that into a tack signal. Tack's not working. Okay, for testing the tachometer, I'm going to hook my drill up to the sensor, and I'm going to power up the gauges, and I'm going to record this on my phone because I can't be both places at once and there's only one of me. So start recording. All right, let's see what we wind up with. Okay, now let's go look at the footage. Oh, yeah, we are getting... Okay, so the tachometer sender is working. All right, I think I need to take that off. I can't get a good look at it there. Let's take it off. Get to take that tube off too, but that shouldn't be a problem. All right, so this is a simple 90-degree drive here, and you can see that it works. If I turn this, it turns the upper portion. And that should fit. There's a little bit of slop in there, but it should be enough to engage in the drive. So, tachometer sender adapters. So this plastic one is what we were using, and it's just too small, basically. And if you look at it, you can see this one is ever so slightly bigger, just big enough that it won't rotate and turn inside of the port. If you look at this, you can see there's no way for it to turn in there without turning the tachometer. It can't, whereas the plastic one, because it's plastic, it can. The problem with this one is it's too long. If we try to put our actual tack adapter on there, no luck. Okay, well, after making it much smaller than I had bargained on, that is our homemade adapter, which works. All right, so the only thing remaining is to put this back together and make sure that everything actually works when it's all together. All right, okay, try this again. Okay, so nothing we did worked. So here's the old, this is either the speedometer cable or this is the speedometer cable. It has the square end drive, but this is like an intermediate cable made for use between two others. So it has the drive on one end, the female, and of course the male on the other. I'm going to clean this up, clean the cable housing. This will allow me to bring it out so I can actually see if it's turning, and then I'll know at least. And it'll also allow me to get the adapter away from the, not the adapter, the sensor away from the exhaust if it works. I don't know. Let's see if this helps with our troubleshooting. And clean this up. So we've got this cable installed, so we should see this turning if everything is according to plan. If it's not turning, then that means we're not getting good engagement. Yeah, so it is turning. I don't know. Let's play around a little bit. Nothing. Goes forward. Try reverse. So the second one is really what we want. Just counterclockwise. All right. Turn that off. Let's see what we have. Forward. Reverse. And that is a nope. It does not work in reverse. All right. So just in a quick test, we can verify some things here. So the output of this sender is the green wire. I have that hooked to the positive lead of my meter. The negative lead is to the ground, and I have power and ground hooked up to the sensor as well. Now, we know it generates a signal, which is a pulse, which I think is a DC wave. It's just like a DC square wave, but I'm not sure of whatever amplitude. It doesn't matter because it's counting the frequency, which we can't measure with this. But we can see if it's generating that signal, that wave, in both directions. And if it's negative in one direction or the other. So right now we're getting 29 millivolts, which is just a trace signal. So we've got our drill set to clockwise. So let's run this. So we get about 6.2 volts DC. Let's run it in reverse. About 6.2 volts DC. So we're getting outputs in both directions. It's outputting, and it's outputting the same positive, like it's not like switching to a negative signal or anything in the reverse direction. So there's our pulses. Let's run it in reverse. Exact same output. So that's about 1500 RPM on the drill there. So anyway, if you've ever wondered what one of these sensors for a tachometer or a speedometer looks like, that's what the waveform looks like. Now, there's one thing I hadn't considered here. And if you had considered it, you're probably laughing at me. And justifiably so, because it didn't occur to me. I don't know what the gearing of this old tachometer was, meaning I don't know what the gearing coming out of the engine. Is it severely reduced gearing, such that like 500 RPM on the engine only spins that shaft at like 10 RPM, you know? I don't know. If that's the case, it wouldn't even register on my tach when I have it set at the current settings, which is 1:1. So I don't know. Let's spin this with a drill. We know our drill goes 1500 RPM. I don't know. Okay, so here's 1500 RPM at maximum rotation. Oh, backwards. Yeah, I don't know. So 1500 RPM does about 2100 on this gauge. Yeah, no matter what cable we would have used, the tach itself is the jumpy thing. Okay, so at 1500 RPM on the drill, we're getting 2200 out of the tach. Okay, yeah, we're gonna have to figure out what that reduction is. Okay. Okay, so the only difference I could come up with is it's the speed. So that gear ratio in that sender is completely different than what I thought. So what I have to do is recalibrate this tach. So it's a little high, a little low right now. So obviously we know the speed is different and we need to make it lower than that 16 pulses per revolution because we're running at camshaft speed, because I was an idiot and I didn't think about that before, but now we know it. So I figured I'd take that 16 pulses that the factory is spec'd at and have it to 8, and we'd be roughly in the territory. And we are roughly there, but it's not accurate enough, it's not close enough. We need to figure out what that final number is, and we can't really do it by counting gear teeth easily because I don't feel like taking the engine apart again. So we're going to try to figure it out through basic math here and what we know, and maybe we can get it close enough to work. So let's see what we can do with that. So let's look at some ways we could calculate this just based off of what we know and some basic math and just the data we have on hand. So we know the original mechanical tachometer speed. We know we can figure out the driven ratio because when we put in a known speed of 1500 RPM, we get out 2200 RPM, and that's a 0.68 to 1 driven ratio. Now your standard crankshaft to camshaft ratio is 1 to 2, so the crankshaft spins 1 time and the camshaft spins 2. However, we don't know if this gear that's driven off the camshaft is spinning at 1 to 1 with the camshaft, because we can't really get in there to count gears properly. We can count gears on the one side but not the other. Basically, I can count the gears, I can count the gear teeth on the unit that's being driven by the gear on the camshaft, but I can't really count the teeth on the camshaft properly, and not without a lot of work anyway. And I'm not opening the engine again, and I can't find what they're supposed to be on any diagrams or manuals or anything. Now there is the possibility that this mechanical tachometer didn't come with this engine, is calibrated for something different, or is just wrong or incorrect. But there's also the possibility that it is calibrated correctly for the gear ratio that is being output. We don't know that for sure, so we're going to set this data aside for now because we don't know if it's accurate or not, but it is data that we have. So now let's look at the digital sender that we're using. The factory says it should output 16 pulses per revolution. To test that, we've used an oscilloscope we need a speed reference for that. So when we spin it with our drill, we're spinning it at 1500 RPM. So that is the comparative speed reference we're going to use. So when we spin that at 1500 RPM, we should get 24,000 pulses per minute. And the way you calculate that is 16 pulses per revolution times 1500 revolutions per minute. You get 24,000 pulses per minute. So we need to convert that into seconds because our frame of reference on our oscilloscope is 1 second, not a minute. So you just divide that by 60 and you get 400 pulses per second. So that's what we should be getting from the factory sender when we hook it up on the oscilloscope. So what we're actually getting on the oscilloscope is 590 pulses per second. We need to convert that into pulses per revolution just to see kind of how far we're off. And to do that, we can see that 590 pulses per second equals 35,400 pulses per minute. And then if we do the calculation at our RPM that we're using, which is 1500, we get 23.6 pulses per revolution. So this, according to what I'm seeing on the oscilloscope, if we count the pulses both above and below the 0 volt line, we get 23.6 pulses per revolution. However, based on what I'm seeing, I don't think that it's counting all those pulses. I think it's counting half of those pulses. So when we have that to get what I think is the actual output for the sender into the tachometer, or at least what the tachometer is reading from the sender, we get 295 pulses per second, or 11.8 pulses per revolution. Obviously we can just have all that data and that's your end result. So looking at what we know, let's start with the original tachometer. So that ratio was 0.68 to 1. So when you have a standard crankshaft, camshaft, in this case camshaft and sender because they're driven off the same camshaft ratio, it would be 2 to 1. So one turn of the crankshaft basically equals a half turn of the camshaft, or in this case the sender. So when we use our reference speed of 1500 RPM, the camshaft's actually spinning at 750. So to compensate for that, when we're looking at a speed of the crankshaft, which is our engine RPM, and we add in a ratio of 1 to 2 to speed it up again on the actual gauge. So if we believe that that original tachometer compensation is correct, by adding in a 0.68 to 1 ratio and speeding it up again at that rate, then we need to assume the original crank to sender drive ratio is the opposite of that, which is 1 to 0.68. So just for test purposes, if we back into this and figure out how many pulses per revolution that would be reflected on the gauge, if that was a digital gauge, the setting would be 10.88 pulses per revolution. Now that really doesn't help us because that gauge is mechanical and we're looking for digital, but it gives us a little bit of a reference. So let's see what we can do with that moving forward. So regardless of what this sender is actually supposed to put out, we know what it's putting out because we checked it. So if we assume that the standard crankshaft camshaft ratio is 2 to 1, and for every one turn of the crankshaft our sender is turning half as much, and then to speed it up again we have to add that same 1 to 2 ratio back in, then for every 11.8 pulses that we are observing we should actually need 5.9 at the sender, and then that will reflect the actual crankshaft revolutions. The thing here is we don't know if this is a standard 2 to 1 output because of those gears that are coming off the camshaft that I mentioned earlier. So we don't actually know for sure what that ratio is. But if we use that data and then we go back and put in the original tachometer ratio, which we think might be more accurate maybe than a 2 to 1, I mean there is the possibility that it's accurate because it could very well be calibrated for this engine. So if that's the case, if we suspect that 11.8 pulses per revolution is supposed to reflect 1 crankshaft revolution, then we use the ratio of 0.68 to 1 instead of 0.5 to 1, then our pulses per revolution at the sender that we need to input for the calibration is actually 8.024. Of course we can't put that in, so it's going to be slightly more than 8 basically. So what I'm thinking here is we're probably actually closer to 9 if we compensate for a little bit of maybe variation in our math and things. So we're going to enter 9 into the speedometer and see what it looks like. Okay, so that's at about 8. Close, maybe? Okay, so we need to figure out how to calibrate this tachometer, but I can do all kinds of math, but at the end of the day I'm not sure if it's right because I'm not sure if my base numbers are accurate, like gear ratios and all that stuff. So another solution is the tiny tach, and if you're not familiar with it, they have a special option for diesels that uses a clip for your fuel line, and it will basically measure fuel line pulses. Now the closest they had to this is 1/4 inch. It's still off by maybe like probably 1/100 of an inch roughly, but I believe that it will be close enough, but we're going to find out. We're going to hook this thing up, we're going to see if it works, and if it does give us a reading, it'll give us a direct RPM based off of fuel pulses, which aren't going to lie basically. So I don't know, let's see if we can hook this up. put this on the fuel line and then just kind of temporarily run this into the cab. Let me show you what we got here. We have the actual box unit hooked up to power, which goes right to our battery because this is temporary. We got the tach unit on our #1 injection line. I don't know if that's tight enough. There's a little bit of crack there, I'm not sure. And this goes to an engine ground. I don't know if that's gonna work, because like I said, I had this is like a metric fuel line or something on here, and the closest they have like, you know, 5-6 millimeter, and then they have 1/4 inch, and the 1/4 inch was the closest. Okay, 738. Actually, that's pretty close. 743. That's very close. It's not warm yet. So my tuning, just by calculations and trying to figure out roughly what it should be, I think succeeded. Okay, I think we got a working tach now. Well, working and accurate tach, that's good. I don't know, it's still pretty obnoxious. We may have to add another muffler to this thing, but we got plenty of space to add another muffler if we need to. Part of the reason it idles so weird is the spring is still not quite tight enough on the throttle plate. But it's fairly cold out. She's not really spitting out much smoke. There's a little bit because it's cold, but other than that, it's pretty good. We are definitely going to need some Dynamat, serious insulation in this cab, because it is just echoey. It sounds completely different in here as opposed to out here. I do like to hear this baby purr, but I don't like the echo effect when she does, if you know what I'm talking about. So let's see what the tach is currently set at. The way you do that is you got to reach up behind, press the button, or press and hold for 3 seconds. Okay, so we are currently set at 9 for a step interval, which is essentially the pulses per revolution. Okay, so we've got this all wrapped up. Our final tach configuration is a cable coming from the sender directly into the mechanical sender, coming directly into the electronic sender for the gauge. This will go around our, get that out of the way. Let's go around our brake booster, okay, I think. So I know that most of what happened there was incredibly boring, but let me break it down for you. And a lot of this was cut out due to it would just be too incredibly boring to show on video, and I went through a lot of dead ends trying to do this, and you'll kind of see some of them I was heading for a dead end, but I didn't bother covering it. So one of the dead ends that I went down was I wasn't 100% sure that the tach drive was spinning due to all the adapters I had to use and everything to get it to the digital sender. Another dead end I went down was the direction. This tach, for whatever reason, seems to only want input in the clockwise direction, and I had thought that it was spinning clockwise, but I was looking at it wrong. It actually was putting it in the direction it needed it, so I got lucky there. Even though I'm not even remotely sure why this tach won't read the sender in both directions, because as you saw in the outputs with the meter and the oscilloscope, it's basically the same output. So then it hit me that the speed was the issue, which I should have known from the beginning, because it's obviously driven off the camshaft because it's on the side of the block there. But for some reason my brain didn't process that right out of the gate. And it should have been a 2-to-1, because the crankshaft spins twice, the camshaft spins once. But there must be a gear ratio difference in that oil pump drive / tach sender that it's slightly off, because if it was dead on, it should be closer to 8, and it's not. 9 is actually the closer number, and if I go down to 8, it's not right anymore. It's not as accurate. And we know how accurate the sender is, which is to say not very accurate, because we checked that with an oscilloscope, and it all kind of ended up compensating for each other and being closer to 8 than it should be, just because the gear ratio helped compensate for the deficiencies in the sender. So it's actually ended up being closer to 8 than it really realistically should have been with the quality of the sender I'm using. But our end result was the input ratio for the tachometer, which corresponds to pulses per revolution, was 9. That's what we ended up with, and that was the closest that we verified with the tiny tach, which is a pulse directly off of the fuel line. And because that's right off of the fuel line, that's the actual injection cycle. You can't fake that, you can't spoof it. So for real, that is the actual RPM. So that's basically what happened there, even though, like I said, I went down a lot of dead ends, and some of them I didn't even show on camera, trying to make sure all my adapters were working and everything was actually turning and everything, because half of this stuff was never meant to be attached to this tach sender. Well, none of it was ever meant to be attached to this tach sender. It was supposed to be cable drive from the get-go. But it does work, and it is terrifically accurate. The only problem I have with this tach is it has a little bit of a lag sometimes, and it's probably getting electrical interference or something, you know, just because it's a cheaper tach and all that. But we do have a tach that works now and is actually more accurate than I thought it would be. So that's a good thing. And before you all razz me in the comments, because I know you all are heading there now, yes, I'm too lazy to pull the engine back apart and count gears on the camshaft and everything else. Basically what you have to do is pull that tach sender out, put a paint mark on the camshaft, and count the gears as you rotate it. And it's easy to lose count, and you have to turn the engine over twice to do it, and basically it's a royal pain in the butt, and I didn't want to do it because I'm lazy. I'll admit it, I'm lazy. I would rather sit down and do the calculations and try to come close, you know, by shooting in the dark for a couple minutes, and then, you know, spending $150 for a tiny tach to verify, you know, my calculations. Yes, I am that lazy. Yep, there's just no way around it. I've got to admit it. So hopefully that wasn't too incredibly boring. Any time you're retrofitting stuff like this, I mean, this has been a real hot rod project from the beginning, and we're getting really into the nitty-gritty hot rod parts of this thing, because we're retrofitting parts to things that were never intended to be used there and so forth. And the end result is that hopefully you get something that works and works well. And I want something that's going to work really well. This little guy, he wants to be in the video, is what I'm saying. Fly away home, buddy. I don't know why, but they like this truck. They're not nesting in it. I don't know. Maybe because it's yellow. Anyway, if you've been watching all these little probably painfully boring videos that I'm making on all these little parts to get this thing complete and running, thank you very much. I do appreciate it. I never intended it to go this far because I figured it wouldn't be this difficult. I know, it was stupid, but mistake on my part. We've just got one or two more things we need to get working, and we're getting closer. We are getting closer. No one wants to see this on the road more than I do, I promise you. Anyway, if you're watching these, I really appreciate it. Hopefully we can both learn something, even if what you're learning is don't try this at home, because it's incredibly painful sometimes. Anyway, feel free to like, subscribe, hit that notification bell. That does something. And I really do appreciate subscriptions. You have no idea how much. It helps the channel grow. Makes me feel really good. Maybe I'm helping people out or showing people maybe how difficult or how easy it is, depending on how stupid you think I am. But I do appreciate it. So feel free to like, subscribe, comment, and as always, thanks for watching.